Determine the components of the support reactions at the fixed support A on the cantilever beam. So let's start with a couple of assumptions. Let's assume this is a weightless, massless beam. Let's also assume it's a rigid beam, so it can't deform with any of the forces applied to it. And let's also assume it's a widthless beam too. Okay, so a cantilever beam simply means it has a completely fixed support here at A. So the support here can resist forces in the Y, in the X, and moments too. So this beam can't move at all from support A. Start with our find variables. The reaction support at A in the X direction, the force in the Y direction, and the moment that it resists as well. Okay. Start with the free body diagram. Okay. Just label the points. Only given one point right here, just A. So might as well label a couple points here. Let's call it B, and let's call it C over here. And 5 meters. And 30 degrees right here. And 30 degrees here. So at A, we have a reaction in the Y direction, AY, a reaction in the X direction, AX, and we have a reaction to moments too. Let's call that AM. Perfect. At B, we have a 6 kilonewton, a 6 kilonewton point load. And at C, we have a 4 kilonewton point load as well. Okay. Let's start with the sum of forces in the X. Set it equals 0 because this beam's at rest, it's not accelerating in any direction. Going from left to right, we have the reaction to AX, and we have the 4 kilonewton point load over here. And so we need to find the horizontal component for that. So what we're going to do is we're going to take the cosine of 30 right there. So equal to 0. You plug that into your calculator, you should find AX. Should show that we have one unknown in this equation, so it'll be quite simple to solve. You should find AX is equal to negative 3.46 kilonewtons. So all the negative sign here denotes is that in our free body diagram right here, I wrote the force vector in the wrong direction. AX will actually be acting towards the left right here. It's not a real big problem. Let's write a note. Force is in the opposite direction than shown in free body diagram. Force AX is opposite. And also, it's important to note at this point, you shouldn't change your free body diagram because your equations work with it, and you don't want to change it after the fact. Let's write down our first known. I am going to drop a sign on it, though, because the sign is kind of, it's unimportant, really, because it just symbolizes the direction right here, and it's really asking for the magnitude in this question. So let's continue on to sum of forces in the y. Set it equal to 0. Left to right, we have the reaction of A at y, in the y direction. Then we have a 6 kilonewton point load negative. It's going down. And then we have that 4 kilonewton load going down as well. And to find the vertical component, we're going to take the sine of 30. And set that all equal to 0. Again, I have one unknown, so you apply that into your calculator. You should find AY is equal to 8 kilonewtons. Perfect. And we got a positive number right there, so then that simply means that we wrote AY right here in the correct direction. And that'll be our second unknown. Okay, to find the reaction of A at the moment, we'll sum the moments around A. You can sum the moments around anywhere, but I think summing them at A will be the easiest for us. We're going left to right. We have the free moment about A. That's going to be positive, using the right-hand rule. And then go into point B, we have the 6 kilonewton point load, which is going to be negative. It's acting at 1.5 meters away from point A. Okay, so we have to break up the components of this force right here, which is quite complex relatively force right here, because it's on top of it being not aligned with one of our coordinate systems. It's also not it's not like perpendicular or parallel to the point A. So I'm gonna have to split these into components like this, because they both do cause a moment right here. So we know this is 4 kilonewton cosine 30. This would be 4 kilonewton sine 30. And we know the vectors, we can slide them. So we're going to take the horizontal component right here and going to slide it all the way back to over here. And if you see, then we can see that our moment arm is going to be that right there, which is simply going to be 1.5 meters, and it's going to be the sine of 30. Because we're given the hypotenuse right here in this triangle, and we know the angle right here is going to be 30, so if we take the sine of it, we're going to find that height right there, which will be our moment arm. So let's go write that down here. We have 4 kilonewtons. It's going to be cosine 30. It'll be 1.5 sine 30 for our moment arm right there, 1.5 meters. And that's going to be in the negative direction there, using the right-hand rule. Okay. And then for the vertical component, we'll do the same thing. But this time we have to add up the distance right here with the component here in the triangle. Just slide it Should get something like that. And we know this is going to be 1.5 cosine 30 meters. Okay, so I'm going to add those all up. Hmm. 3 meters plus 1.5 cosine 30 meters as well. So that'll be our moment arm right here. And we also know that's going to be 4 kilonewton sine 30. Sine 30 degrees. That would be our force. If we can see, this is also going to be a negative moment right here. I'm going to set that equal to 0. It's a big long equation right here, but we only have one unknown right there, which will make our life pretty simple. To find the moment at A equal to 20.2 kilonewtons meter. And that's going to be our third and final unknown. 20.2 kilonewtons meter. And see, it's a positive answer right there. So this means that we drew this right here in the right direction. That's all it means.